All right. Very good afternoon to all of you. Thank you for joining. My name is Vinay Nair, and I'm part of Raising a Mathematician Foundation. We are an NGO that work in the space of math education, making mathematics more exciting and wonderful for students of different ages, and also for teachers. And we do various programs, starting from Olympiad training to math residential camps, online camps, camps only for girls, math contests, and so on and so forth. Okay. There is a lot of information that you can get from our website, raisingamathematician.com. And there is also a link that you would have received in the Zoom link invite on the email. And that link is of a WhatsApp group. If you join the group, we can share more information about various other programs and you can understand more about these programs from there. Okay. So that's just a short welcome note and we'll get into action directly. Today we have with us Vardhan Bhaiya, Sai Didi, and Dr. S. Muralidharan. We call him fondly as Murli sir, all three of them. And they'll be sharing some fun stuff with you in math. And before they start, let me just tell you that I'm sure it's going to be a lot different than what you would have seen in school. Okay. And maybe some of you are already doing competition math. Hmm? But the kind of problems that they are going to share is to just give you an exposure into what exactly you can encounter or what exactly you can get excited about mathematics when you do Olympiad. Okay. The real Olympiad and not the popular math competitions that go by the name Olympiad. Okay. So that's a short introduction. Welcome all of you on board. From here, I'll hand it over to Vardhan. I guess, Vardhan, you're going to start, right?
Yes.
Yes. So over to you, Vardhan, and best wishes to all the participants.
Thank you, Vinay. So let me start sharing. Let me start by sharing my screen. Hello, everyone. So this is the first lecture of this workshop, which is about computational thinking. So before I even, okay, one second. Can you guys hear me? Can everybody hear me?
Yes.
Okay. Thank you for the confirmation. So before I start, just wanted to see how many of you have ever heard about like programming and computational thinking, just as a word, not the meaning or something. Just give a thumbs up. Okay, there are a lot. Nice. Yes. So how many of you know about Informatics Olympiad in India? That's nice. I came to know about my about Informatics Olympiad when I reached my college. So it's really good that you guys already know about it. Yes. So the whole idea of Informatics Olympiad, at least within India, it's about computational thinking. So we do maths, you have formulas, you have equations, you solve something. But computational thinking is the addition on that in a way that you have to do these kind of calculation on a system, on a computer system, right? So you cannot have like infinities. You cannot have you don't have enough resources because the computer system has only finite memory and finite time to compute things, right? So it's just a constrained version of mathematics where you have to even think in a way so that you can compute things faster. So that's one of the aspect of computational thinking that we will see. So before I even talk about computational thinking, I will talk about the IOI structure, which is the International Informatics Olympiad, International Olympiad of Informatics, and we will see what are the levels that you need to qualify within India to reach here. So the first round is ZIO and ZCO. So that is Zonal Informatics Olympiad or Zonal Computing Olympiad. So they have a different structure, which I will talk about later. So this is the first round, and the number of people who get selected is capped to 200 to 300. It depends; it changes with year to year, but I think it's capped to 200. I have written it 300 here. And after that, there is a national round known as INOI, from where 30 people are selected for a training camp. So this training camp usually happens in Chennai Mathematical Institute, where I'm doing my master's right now. So here people are trained to do harder problems so that they can tackle the question papers which is set in IOI, which is the main aim, International Olympiad of Informatics. So ZIO and ZCO,
Sorry,
they,
Vardhan, can I just interrupt
yeah,
over here
yeah,
in this slide? Yes. So I would also want all students to look at the numbers. Okay. As much as Math Olympiad is popular in India, the Informatics Olympiad is not that popular in India. And through both ZIO and ZCO, only around 300 students get qualified. So yesterday or day before, the ZIO results came out, and I'm so happy to share that there are 25 students from Raising a Mathematician Foundation who qualified through ZIO. Now, ZCO is yet to happen, but these 25 students are going to write the national round. Just wanted to mention that. Sorry for the interruption, but then please.
yeah. Thank you. Yeah, so there's a difference between ZIO and ZCO. The thing is, for one of the exam, you need to know programming in either Python, Java, or some other coding languages which are stated on the website. But for one of them, you don't need. You just need pen and paper and your brain. That's all. So that level is ZIO, where the questions are very much related to computational thinking, algorithmic, and it's basically problem solving through mathematical skills. But it's just pen and paper. You don't need any coding skills till then, and it's a 3 hour paper. But for ZCO, which is the Computing Olympiad, you will have a computer system where you will actually code and do the you will solve the question. It's like a format of a programming contest. But the ideas behind both of these exams are very similar. So you need to master in computational thinking. And yeah, these are the later rounds, which we will see later. Yes, let's come back to computational thinking. So I will just read out the slide first. So computational thinking is a problem solving approach that involves formulating problems in a way that enables us to use computers or humans to solve them effectively, right? So this is what I stated earlier as well. So there are most of the problems that we solve in computational thinking is very similar to what we do in maths. But the thing is, there's some kind of constraint, right? Computers cannot deal with infinities, and there's a restriction on the amount of space that you have. You can write a lot of formulas and stuff. You can just state these there exist some formulas and all. But for computer, you have a bound on the memory, so you cannot write anything infinitely many times. So that's the issue. And then like four steps that you need to follow in computational thinking. First is decomp. So once you have a problem, you first try to see, can you break down these problems into some parts so that each of the part becomes simpler. So that is known as decomposition. After that, in order to solve a problem, so when you see a problem like in your book, in a school book itself, you see, okay, this question might map to this formula, so I might think of this formula, right? So that is known as pattern recognition. So have you seen that problem somewhere, or does it look very similar to a problem that you've already solved or a formula that you've learned, right? That is known as pattern recognition. After that, there is something known as abstraction. So abstraction means instead of just looking at like a real word problem, you try to abstract it using symbols, right? So you might have seen like word problems like Ram has bought these many apples and sold it at this price, right? So instead of like looking at it as a, like who has sold and who has bought these apples, you just write it in terms of symbols with plus, minus, multiplication, and all. That is not an abstraction. So the language of mathematics is abstraction. And after that, in order to solve this effectively, right? I have written this word effectively, computational thinking. You have to think algorithmically. So in the sense like how to reduce the number of computation, even still you are getting the same output, right? So with decreased number of computation, you can still get the same output that you want. So that is the algorithmic design. This is where you need to think. This is where it is different from mathematics. This algorithmic design. Yes, I have already explained these four steps. Yes. So why computational thinking is essential for Informatics Olympiad? I mean, the base itself is Informatics Olympiad, but the main thing is the problems are not like the math Olympiads that you see, right? It's not like you do some brute force stuff. So brute force means you just calculate everything. You with the idea that you have, you also need to think of the idea so that you can do it effectively on the computer system. So there are a lot of algorithmic techniques. I'm not going to define them, just stating them here, which is recursion, dynamic programming, greedy, and divide and conquer, which we use to solve problems. So these are the algorithmic techniques. And the problem domain. So in math, we learn a lot of topics, but for computational thinking, you don't need to know a lot of things. You only need to focus on combinatorics, graph theory, number theory, optimization, and data structure. That's all. So the amount of formulas and everything that you need is very limited, but the way you have to think to solve the problem is what is important. So now I have explained what is computational thinking, what is the structure of Informatics Olympiad in India. Now we're going to solve some problems. So I'm going to show you the problem. I will give you some time to just read and understand the concept about it. And maybe you can try to give me ideas before I discuss the solution. So we're going to solve this problem number 2 first. So this is the problem. So I'll just give you 2 minutes to read through it. So the question itself starts by defining something new, right? It says an integer is solid if it is positive and does not contain the digit 0. So you have some number of digits, and when you write it from right to left, if it doesn't have 0, then I call it solid. So I have given an example as well: 115, 1223, 4 times 9. These are like solid integers. So they don't have any 0 when you write them, right? But 10 is not, because there is a 0. And what is the sequence? I have written a solid integer sequence, but you also need to understand what is a sequence. Sequence is just a list of numbers where we have given an ordering, right? So in this sequence, I have written 1, 2, 3, 4, 5, 6. So 1 comes before 2, 2 comes before 3. A sequence is just a list of numbers where there is an ordering. So I can tell what is the first number in the sequence, what is the second number in the sequence, right? So here the 10th number in the sequence is 11. And in this sequence, the nth number gives me the nth solid integer. Because the 10th integer is 11, so in the sequence, so the 10th solid integer is 11 because it's the solid integer sequence, right? So we have seen two definitions. One is the solid, what is the definition of solid integer, and what is the sequence, right? And my aim is to find the nth solid integer for n is equal to 100, 2000, and this is 1 lakh, right? But these are bigger numbers. Let's try to understand it for a smaller number. So for 10th integer, I think it makes sense. For the 10th solid number, it makes sense. It's 11. Okay, people have raised their hands. I don't want the answer. If you have something to discuss, sure. Let me see who are there in the raising hand thing.
You will have to unmute them, Vardhan, or you can
Okay,
call out their name and one of the volunteers can unmute them.
okay,
There is Sriram.
yes. Sriram.
Go
Yes,
ahead, Sriram.
yes, sir. Am I audible?
Yeah.
Sir, so the pattern comes as follows. Like the 10th solid integer comes like 11, 20th comes as 22, 30th comes as 33, and goes on 11, 22, 33 as multiples. So if you want like 100th, we can just do 11 into 100, like, which is like 1100. 11 into 2000, which is 22,000, and 11 into 1 lakh, like that for n.
Okay, that's a good start. You try to find that pattern recognition. You try to find that pattern. That was the second step. You are right for some set of integers, but not for everything. But that's the correct step. So for the first, I think 99 digits, it will work. Your algorithm, your pattern, but this might not work for bigger numbers. Yes, let me hear Saranya Harikumar.
So we see the pattern that the 10th solid integer is 11, the next number. So 20th solid integer is not 20 and 21. And 30th solid integer is 31. So the pattern goes like this. So the if n equal to 100, then 100 after 100 till 110 it has 0. So 111 will be the solid integer. And for n equal to 2000, n equal if it is 2100 also there are two zeros. So the answer for that is 2111, and the next one is 1,11,111.
I see. I get a point. So it just needs slight refinement. Let me hear somebody else as well. Hemdev, Krishna.
Guys, when the names are called, can you quickly unmute them, please?
Sir, sir, in the first one, I already did this problem. So, the first one, yeah, 11 is the 10 solid integer. 22 is the 22nd. 33 is the, if we go until the 90th solid integer. Wait, what? 90th solid integer. We'll get 99. But
90th
there's
solid
still,
integer. Yes.
yeah. So, which means that we can, but after this, we have to skip from 100 to 100, 110. So, which means we'll just ignore those values and then go to the next. From 110 to 120. As 110 and 120 don't count, there are 8 solid integers between. Right.
There would be
So
9, but
let's
you are
just
correct.
count how many these solid integers from here. 111, 1. If we count, we'll get 121. If we count, is the 100 solid integer.
Yes.
If we count till that point. I tried to do that method with a little different for 2000 and 1000, but I didn't understand. So I'm trying to find another method.
What you did for 100 is correct. We will try to generalize as well. First, we have found the pattern for a smaller set of integers. Yes.
So we got a 121.
For 100, yes. That's correct. So let me try to explain how do we get 121 for 100 as
Vardhan, I think you went on mute.
Oh, sorry. I was just speaking. Yes. So let's just see it for 100. How do we get it for 100? What he said is correct. And we will try to generalize it for bigger number. Right? So what is the...
Vardhan, can I
Yes.
just
Yep.
Suraj's internet is down, so he's not able to unmute the participants. So whoever you want to unmute, can you unmute them directly?
Sure. Yeah, that works.
Okay. Same for Sai, and when Murli sir is doing, maybe one of you can help them. Yeah.
Okay. So let's just see it for 100 and then we'll try to generalize the idea. Right? So the first 9 solid integers are 1 to 9. Right? After that, we get a 10. So we just skip it. And the next set of 9 solid integers are from 11 to 19. Right? So in total, we get 9 plus 9, 18 solid integers when we count from 1 to 19. And similarly, from 21 to 29, we get 9 more integers until 91 to 99. We have accumulated 90 solid integers, right? From 1 till 99. Okay, let me change the color. Sorry for that. Yes, from 1 to 99, we get 90 solid integers, right? But after that, we see 100 has a 0. From 101 to 110, we again have at least 1 0 in each of them. So what we do now, we start counting from 111. From 111 to 190, we get 9 more integers. So we get 9 more integers. This will give us 99 solid integers. So we have counted from 1 till 190. Now 120 again is not a solid integer. So we go to 121. And this will give me the 100 solid integer. Right? Right? So can anybody tell me how many 3-digit solid integers are there? 3-digit solid integers. There are 9 single digit solid integers and 81 2-digit solid integers. How many 3-digit solid integers are there? You can write in the chat if you want. I have typed out the question as well if somebody couldn't hear me.
Vardhan, the chat has been disabled for them.
Okay, got it. Okay, somebody DM'd me. Yes, so the answer is 729. So let me discuss why. So you can see the pattern, right? So for single digit, you have 9 power 1, 9 power 1. For two digits, you have 9 power 2. And similarly, for three digits, you will have 9 power 3 solid integers with number of digits equal to 3. I must have mentioned it in the next slide as well. Yes. So they are exactly 9 power d solid integers with exactly d digits. So this is a pattern that we have found, right? Now I'm going to state an algorithm, actual generalized pattern. I'm not going to discuss why that works. You have to fill out the details, but it's not very hard. It's not very hard to see why it. So what I'm going to do, just give me a second. Yes. So I'm going to find. So for 100, let me just write it for 100 so that we see the pattern, what happened. So for 100, we first selected the first one digit, the first 9 one-digit numbers, and then we collected the two-digit number, right? Still, we couldn't reach 100 in some sense, right? But as soon as I add 9 power 3, this sums exceeds 100. So that means the solid integers, the 100 solid integer must be between this 9 square and 9 power 3, right? That's the idea. So I will find that number, so which is this. I'm going to find that d. So I'm going to find the smallest d such that 9 power 1 plus 9 power 2 plus 9 power 3 till 9 power d is greater than or equal to n, right? I will find that integer d, positive integer d, right? Now, what I'm going to do, I'm going to find the cumulative sum from 1 till d minus 1. So for 100, my d is equal to 3. So now I will find the cumulative sum from 9 power 1 till 9 power d minus 1. So this is my cumulative sum, which would be 9 power 1 plus 9 power 2. And this is equal to how much? 81, right? How many steps still I need to climb? I need to climb 100 minus 81 steps, right? So I need to climb, the steps that I need to climb is 100 minus 81 in order to reach 100. So this would be equal to 90, right? And the pattern that the main thing in this algorithm is we are offsetting it by 1. And this is a question that I will leave to you why we are doing it. It's not very hard to argue, but what I am doing is the number of steps is this, right? Which I have written 100 minus 81 is this, but I have subtracted a 1 as well. So that you're going to fill up, that you're going to fill with the reasoning, right? So what I do now, I write this number of steps in base 9. So let me go to the other slide. Okay, let me write it here itself. That is the actual algorithm. So I first find that d, so that summation from that to 9 power d is greater than or equal to 100. Then I find the cumulative sum for from 1 till d minus 1. Then I find the offset, which is the number of steps that is needed to go from from the cumulative sum to n, right? Which is 19 per 100. Now I write 19 in base 9. So what is 19 in base 9? So this number is written in base 10, right? So everybody understand bases, right? Base 10, base 2, base 3. If you know, can you give a thumbs up? Because I assume you guys know that. Okay, great. Yes. So what is 19 in base 9? If you can calculate. Yes, I have got the answer. Okay. Oh, sorry. I made a very big mistake here. The cumulative sum should be 81 plus 9, right? What is 9 power 1 plus 9 power 2? That is 81 plus 9. So let me correct that. Sorry for the confusion. So this should be 81 plus 9. So the number of steps which are left to reach 100 is actually 10, not 19. right? So 10 in base 9, 10 in base 9 is actually 11, right? 10 in base 9 is actually 11. But as for with my algorithm, I have to find the baseline of the offset. Offset is the number of steps minus 1, which is 10 minus 1, 9. And 9 in base 9 is 9 in base 9 is 8. So this is 8. So I have written the notation also. Let me come to this example. Yes. So I found the cumulative sum 9 plus 9 square, which is 90, right? I have got the offset. So this is 10 minus, sorry, 9 minus, 1 second, there is a issue here. Yes, Hemdev, do you want to say something? Let me unmute you. I think you can unmute yourself. I am not.
I've done
Sir,
that.
I want to tell you something.
Yes, please.
Base 9 in base 9 and base 9 is actually equal to 10 in base 9, not 8.
Right, right. You are correct. I don't know. There's some issue with the calculation. Yes, it should be 10. Correct. Right? Yes. So what I do? So my cumulative sum from 9 power 1 to 9 square is 90. So I get this 90. Now my offset would be 99 minus 90 minus 1, which is 8. So why did I write this 99? Okay, I still need to argue why did I write this 99 because I'm okay. This is worked out for example for 99. Okay, sorry for that. So let me do it for 100. So for 100, you will get 100 minus 90 minus 1. So you will get the same cumulative. So you will get 9, which is 8, right? As you said. Sorry, 10, as you said, which is 1, 0. So what you're going to do now, because your d was equal to 3, when your d is equal to 3, you write 1 3 times. Okay, you write 1 3 times. Your original d was 3. Now you have, this is the thing which I have written in base 9. Just write it below that. So I will write it below here and just add it. Just add it normally. Don't do anything. Just add it. So I will get 1, 2, 1. Right? I think Haim they pointed and others also pointed out. The answer for n is equal to 100 is 121, which is correct. So what I do, I find that d so that 9 power 1 till 9 power d is greater than equal to n. Then I find this offset, which is n minus cumulative sum till d minus 1 minus 1. I find this in base 9. Okay. Then I write 1 d number of times. So here d was 3. I wrote d. I wrote 1 3 number times 1 1 1. Then I just added the base 9 sum to it. So I added 1 0. So okay. So let's just do it for a small example as well. Sorry for the confusion. I forgot I have written an example of 99. I forgot about that. So for 25, what is the d? Can you tell me what is the d? So 9 power 1 till 9 power d should be greater than equal to 25. So can you tell me what is the d here? Let me erase this. Otherwise, this might create confusion. Okay, so let me help you. So 9 power 1 plus 9 power 2 is 90, right? Is 90. And this is greater than equal to 25. So our d would be 2. But if you take d is equal to 1, this won't work because 9 is less than 25. So d is equal to 2. You just write 1 1. You write 1 twice, right? And what is the offset? Offset is calculated as 25 minus 9 power 1 minus 1. And how much is this? This is your, this is equal to 15, right? And what is 15 in base 9? Can anybody tell me? You can DM me on the chat. That would be easy. Yes, I'm getting the answer in the chat. Thank you for that. Let me see. Yes. So 15 in base 9 is 16. So I will write 16 and 9. So what will I do? I will just add the 16 here. And the sum would be just, you add normally. You just don't care what is the base. You just add normally. You will get 27. So 27 is actually the 25th solid number, right? And similarly, you can do it for any number. Doesn't matter how big it is. So for 2000, the D would be 3. I'm not doing the calculation. D is 3, which sums up to 819, which is greater. Oh, 1 second. Yes. So D is actually 4, not 3. D is actually 4, which is this. But D is equal to 3 is 819. That means D for N is equal to 2000 would be 9 power, should be equal to 4. So you write 1 4 number of times, right? And what is the offset? Your offset is 1180. And that in base 9 is this 1151. Now you just add this 1551 and you will get 2662. And this is the 2000th solid integer. So you just follow this algorithm. There is, and you only need to find that D. You only need to find that offset and just find that in base 9 always. And this will work. So the answer for 2000 is 2662. And similarly for 1 lakh, your D would be equal to 6. So you write 1 6 number of times. Then you write the base 9 of the offset, which is calculated as n minus cumulative sum till D minus 1 minus 1. And just add it to it. And you will get the nth solid integer. Is there any doubt in this method? You can raise your hand if you want to. Siddharth, do you want to speak up?
So actually, I had a small observation
Yeah.
here. So if a number ends with two zeros, then it's like solid integer is a palindrome.
Sorry, so your conclusion is if a number in base 10 ends with 20,
Yes.
then
Is the solid integer of that number a palindrome?
I'm not sure about that that argument. I mean, I'm not sure about that theorem, but it's interesting to see. So what is he saying that if a number in base 10 has double zero at the end, then the the solid integer corresponding to that n should be a palindrome. Let's try for 1000. 1000 also has double zero at the end, right? It has two zeros. Correct? What is the D for this? Can you tell me? We have already seen that D previously. Let me see the D. No, D should be 4, right? Because as you see, for D is equal to 3, it is 890. So your D would be 4. And can you help me calculate the offset? So I write 1 4 number of times. My offset would be 1000 minus 890 minus 1, which would be 180 for 1000. So for 1000, my offset would be 180. And what is 180 in base 9? 118 base 9. Okay, let me calculate it. So 182. Okay. So 118 base 9 is 210. Right? And when you sum this up, you will get 1, 2, sorry, 2, 2, and 1. Okay, so your hypothesis is still true. I have still not found a counter example, Siddharaj, right? It could be true. I have not proved it yet. For 1000, I'm still getting a palindrome, right? Kavinan, do you want to say something? Let me try to unmute you.
So can you just like explain it again, the whole, like the starting part?
Yes, yes, please. Yeah. So what you do, okay, let me clear the screen. I think I made it too cluttery. So you find a d such that 9 power 1 plus 9 power 2 till 9 power d is greater than equal to n,
Okay.
right? So for 100, that d would be 3,
Yeah.
right? Then what you do, just do the cumulative sum from 9 power 1 till 9 power d minus 1, not d minus 1. You just find how many integers are still left that you need to cross to reach that thing, right? To your actual nth solid integer. And I also do a minus 1. So as I already told you, you have to see why do I do minus 1. It's not very hard. So now what I do, I write this offset. I call this as offset. I write this offset in base 9.
Yeah.
So what I do, I write one d number of times, the original d number of times. Then I write the offset below this in base 9. And I just add it up normally. I don't care what is the base or something, just add it up normally like what we do in base 10. And that will give you the nth solid integer.
Okay.
Yes,
Thank you.
yes, same day.
Sir, you did a decision mistake. 11111 plus 1111 plus 210 is equal to 1321, not 1221.
Could you tell me the example? Yeah, that is very possible. I do a lot of calculation mistakes. That's very possible.
And I think that the theorem is a number which ends with an even number of zeros. Exactly, no extra zero to make it odd.
Okay.
Has a palindrome as its solid integer. That is the remade version.
I think you're talking about this, right? Yes, it's correct. It should be 1321. So there is a counter example for this. So I'm not sure what you claimed is correct or not. What is he saying? If the number of zeros at the end are even, then you will get a palindrome. That could be true. Could be true. Yes. Yes. Is this clear? For the next example, I'm not going to discuss in detail because I think the next session will start soon. I will just take 5 more minutes and try to explain you. It's a different kind of problem. So here I was just using some very basic number theory and pattern matching, right? There was no algorithm as such. I wrote an algorithm, but it was mostly pattern matching. There was no like an actual algorithmic technique. Right, so this is the problem. Just read through it. I will go through the example one. Just take a minute. So what is a binary string? Binary string is just a sequence of zeros and ones. And we've already seen what it is a sequence, right? So that is just writing zero ones in some ordering that gives you a binary sequence or a binary string. And concatenation I just denoted by plus. It is not important for the question, but I'm just to write 0 1 plus 1 0. So you're not seeing it as a number, right? In the previous question, we were actually adding them, right? But currently we're not seeing them as a number. We're just seeing them as a string. So in strings, what we have, I just write it close to each other. So just remove the plus and just paste them together. That's known as concatenation in string. So a string is a very important concept in computational thinking. So as we will solve problems through the workshop, we will see how this helps us to simplify problems in some way. Right? And what is the power of a string? Power of a string is defined as, so if this is my string 1 0, if I write suppose 3, okay, the power is 3. So unlike numbers, it's not like I'm multiplying them. I will just write 1 0 1 0 1 0 3 times. I'll just paste that. That is known as taking powers in string, right? So as you can see, the definitions are changing, right? It doesn't work like numbers anymore. Now this is a definition which is with respect to this question. Any string of the form 0 0 1 1 power k is a good string, right? So an example of that is just that string 0 0 1 1, and the value of k for that would be 1. For this string, I have just repeated it twice, right? I just repeated it twice. This is a concatenation of the same string twice, which is a power 2. And this is also a good string. And similarly, this is just k is equal to 3. Now, suppose I ask you a very simple question. I have 1, 0, 0, 1, 1, 0. Can you tell me a way to remove some of the numbers in this string so that it becomes of this form? It becomes of this form. It follows this form. So let me pick someone new. Tashan, do you want to speak up? Let me try to unmute you. Tashan Sagar. Yes.
I couldn't I couldn't understand the second problem too, the before one.
Problem 2.
Yeah.
What couldn't you understand?
I couldn't understand why do we use 9 as a base? We can use any other number.
Yes. The thing is, we want to avoid 0, right? So that the idea is we want to avoid 0. So in base 10, how many digits I have? I have 10 digits, right? So when I don't want a digit, I just remove that digit. So the number of digits that I can use is 9, right? So the idea is because I can only use digits, 9 kind of digits. That's why I use base 9. That is the idea behind it. Nothing else. Yes. So I was discussing this question. So the idea here is, the question is, can you remove some of the digits from this sequence 1 0 0 1 1 0 so that you get a good string. So let me see who have raised their hand. Sriram, you want to speak up?
Yes, sir. Now I wanted to tell the answer for problem 1.
Yes. Can you tell me the digits that you need to remove from the string, make it a good string?
Like, since like I am not that sure, like one is in the extreme left and one is in the extreme right. I don't think we can remove like that, right? Like
You
one
can remove any digit. You can remove any digit. Doesn't matter.
and 0. It's
1
okay.
and 0. So which one will you remove? You have to tell me the position.
One to the extreme left, yes,
Okay.
and a 0 to the extreme right.
Okay. That's correct, right? So let me give you a harder example. That's what I'm going to discuss for this session. Let's do it for A. You have to just tell me a way to remove 0 and 1s from the string so that I get this form 0 0 1 1 power k.
Sir, I also have another doubt about these good strings.
Yes.
Suppose like, can I write any good string as like we have to write 0 0 1 1? Can we write 0 0 1 1? Like, can we just change the order, like split these things, like 1 0 0 1 1 1 0 0 1 1 again 1
Then
1
1.
0 0, like 0 0 1 1 0 0 1 1. It comes like that.
I still didn't get a question. Sorry.
So like zero. What I am trying to tell is that 0 0 1 1 0 0 1 1, right?
Yes.
1 1. So I just removed a 1 from there and I just placed it to the other side. Does that still
No, that is not allowed. So what you are only allowed is you can only remove digits from this to get a good string. You cannot do here shifting and
be
anything else.
only next to next as the form of 0 0 1 1? Then the answer is obvious, like two zeros 1 and 0 1, like to the extreme
Yes.
left. First 3 digits to the extreme right, last 2 digits. Done.
Yeah, I got it. That's correct. So let me hear from Advita also. You want to speak up?
Hello.
Yes.
I had a doubt. Can we do it like 0 1 0 1? Will that be correct?
0 1
Not this
0.
one, but any other if like 0 1 0 1.
So you are changing the question. Do you want something like this?
Yes.
Yeah,
Can
you
it?
can do that. The correct question only says that you can, the good string is defined like this. So that's how we are defining. You can have any of the question. So for this A part, as he pointed out, so I can just remove these three things and the last two one. I will get a good string, right? I can do
Yeah.
that. Now for
Yeah.
the B part, let's see. For the B part, I cannot start with a one. So I have to remove that one, right? So this I have got 0, 0, 1, 1. Now again I have a 0, but this 0 has to be followed by a 0. So I cannot have this 1, right? Now I have this 1. I have 0, 0, 1. Again I cannot have
We
a 0
don't need
because it has to
zero.
be followed by a 1. So again got this 0, 0, 1, 1. And again at the end I had this 0, 0, 1, 1. So I'm done. So as you can see, so the question says you have to remove some numbers from the string so that you get the good string, right? And similarly for let's do the C before we end the session. If we start with this 0, it needs to be followed by a 0 again, right? It has to be double 0. So I will remove this one and I have got 0, 0, 1, 1 again. Again I have got these two zeros, but this has to be followed by a 1. So I will remove this 0. I will take this 1. I will remove this 0. I will take this 1, right? So as you can see, I've got the second block which has 0, 0, 1, 1. Does this make sense? Right? So now I have taken double 0 again. After double 0, I need a 1. But after that 1, I need to follow it by another 1. So I will remove these zeros. I will take this 1. Right? So I have got 3 blocks of 0, 0, 1, 1. Okay, I need to finish up the session. So I will just take a single question and end it. Saranya Harikumar, do you want to speak up?
Sir, actually, I wanted to answer for the C question.
C questions. Okay, this one. I've already solved, right?
Okay, it's okay. I'll lower my hand.
Yeah. So let me erase this so that you guys can take a screenshot as well. I'm removing the solution so that you guys can solve. So the idea is you have to just remove some integer, some zeros and ones to get a string of the form 0, 0, 1, 1 power k. That's all. So the idea to solve this is using dynamic programming, which I have not seen in this lecture. But you can do this very fast and very efficiently in a computer system. You don't have to like do this kind of pattern matching and something every time. Okay, so that's all from my side. Sai, are you there?
Yes, I'm here. Thank you
Yeah.
for the wonderful problems and discussion. We'll
Thank you.
now. Yeah. Can you hear me?
Yes, Sai, I can hear
Yes,
you.
we can hear you.
Okay. Yeah. Thank you so much, Vardhan sir, for the discussion. Now we'll have, let's move on in the interest of time. We'll have Dr. S. Muralidharan talking about some other aspects of Olympiads. We'll be talking about combinatorics and number theory. Over to you, Murli sir.
Yeah. Okay, I'm audible.
Yes, sir, we can
Yes,
hear you.
sir.
Yeah, and my screen is visible, I believe.
Yes,
Yes.
sir.
Yeah. Okay. The previous session was about the Informatics Olympiad, and then I'll be talking about what it is to do for Math Olympiads. So let me give a brief overview of what the journey is. I mean, if you opt for Mathematical Olympiads, what will be the journey like? So we have several stages of selection, and for the first stage, the first stage is what is called the IOQM. This is the first level of selection, in which we have a question paper of 30 questions with 3 hours, and all the answers are 2-digit integers, and then this is actually a mission evaluated question and answer paper. So this mission evaluated, so OCR evaluated. Okay, whatever. Okay, and we have 10 2 marks and 10 3 marks and 10 5 marks questions, and it's a region wise selection. So we have divided the whole India into about 30 plus regions, and each region about 250 to 300 students are selected for the next stage. The next stage is called what's called the regional math Olympiad. This is 6 questions and 3 hours. And of course, here you have to write detailed proofs. And then each question has 17 marks. So total marks is 102 in this case. Again, we have a regional selection. It's not about 250, 300. It will be much less than that. The third one is what is called the INMO. and we have 6 questions in 4.5 hours, 4.5 hours. Again, this detailed proofs are required, and then each question has 17 marks. It's all India selection. It is not the region-wise selection. It's an all India selection. The next stage is the IMO-TC. This is the International Math Olympiad training camp. It's a 3 weeks training camp, and there will be a lot of practice session selection tests, and then 6 are selected to represent the IMO. So this is the usual progression for representing India at the IMO. For IMO for every year. Okay, here in IOQM, if you want, there will be about 1.5 lakh students will be participating, and this will be around 5,000 to 6,000 approximately. Meaning, I don't know the current numbers, but it will be slightly less than that. INMO is about 300 to 400 maximum, 400 or something like that. And this is basically 30 students plus 30. This is 30 is the junior batch and 30 is the senior batch. And from here, 6 students appear. Okay. So now we know that the difficulty level progresses from one to the other, but you don't have to worry at all. And then we will guide you all through, and then right from the IOQM up to INMO and beyond. So let's look at, now that I have explained the question paper pattern and then the exam progression and then the selection criteria and so on. So let's delve a bit deeper into what kind of questions are asked in each level, and then try to find out solutions for those problems as well. Okay. Right. And the IMO finally will be 2 days, 4.5 hours a day, and 3 questions each day, and then each question is 7 points. And there will be gold, silver, and bronze medals cut off. So that's what the final level is. Okay. Right. So what is this Olympiad like? So there are 4 topics: algebra, combinatorics, geometry, and number theory. And then the problems will be of varying type and so on. So this basically the Olympiad content-wise. Now, what is this Olympiad like? How many of you are aware of what Olympics are like? Several of you, right? So do you know approximately how much time an athlete will spend training for the Olympics? It will be years, right? So it will be years of preparation. Even for the normal Olympics, it will be years for preparation. And these preparations are also guided by a mentor, or what is usually called a coach. Similarly, this Math Olympiad also requires years of preparation, at least months of preparation, if you can ask me. And you also need a good coach and a mentor, and for guiding you towards a success of this thing. For instance, all these subjects, you would have seen this in your school syllabus, but when I just introduce you to the kind of problems which are asked in the Olympiad, then you will know that they are far apart from what the school level questions are about. Okay, but again, meaning you don't have to, you can just train, and then as time progresses, you will become adept in solving these kind of problems as well. So the main thing which you have to remember is that just like a Olympic participant, meaning a Olympic aspirant, you should never give up. So never give up. So that is where never give up, and then we will be definitely guide you through all steps on the way. Now, instead of talking about these generics and so on, let me look at one problem from each level. That is one problem from IOQM, one from RMO, and one from INMO, and then one from IMO. So these 4 problems we will look at, and then see how we can cope up with this one. So this doesn't need any special knowledge of mathematics at all. I have chosen problems in such a way that they just require some ingenuity. That's all. You don't have to know any results from anywhere. Okay. So I'm going to look at one of the problems. Let's look at this. I will talk about 2 topics. One is combinatorics and the other is number theory. Let's look at combinatorics first. This problem is from IOQM 2024. We are given 5 points in the plane with no 3 of them collinear. So I have collinear means they lie on the same line. Okay, suppose I have 3 points like this and a line passes through them, then it is collinear. So we have 5 points, no 3 of them are collinear. Now, each pair of points is joined by a line, and of course, I'm going to join all of them, all pairs of lines, all pairs of points. So I can join like this, I can join like this. I have joined all of them. And how many ways we can color these lines, red or blue, so that no three of the points form a triangle with lines of the same color. So for instance, suppose if I just let me color like automatically. So suppose I have, so these 5 points, then I'm going to join some of them red like this, probably this one, and then the other one, let us say blue. I have a blue, this may be, okay, doesn't matter, black. So I have joined this black. Have I left out anything? Yes. Now in this one, can you find 3 points which are the lines joining them are the same color? Can you find in this one? Is there any triangle, that is any 3 points which the lines are the same, meaning same color? So if I take these 3 points, let us say this point and this point and this point. So these two are red, but this one is, these two are red, this one is black. So that doesn't qualify. So there are plenty of triangles here. And do you find any one triangle in which all the 3 are the same color? I think I have to do something. Yes, yes, Sriram. Unmute. I don't know, how do you unmute this?
Yes, sir.
Yeah, okay.
Sir,
Yeah.
I've done that.
Uh-huh.
Sir,
Yeah.
sir, over there, from the left bottom point, you can see a black triangle there. All of them.
Yeah, we have a black triangle here. So we have a black triangle here. But this is not the coloring I want. So
No.
the question asks how many ways I can color these lines with 2 colors so that no 3 of the points are the same color. So let us try one more time. Suppose I have these 5 points. And then I will color this is red, this is red, this is red, this is red, this is red. And say perhaps this is green, so this is black, this is black, this is black, this is black. Now can we find a triangle in which all the 3 are the same color? So this is one coloring because there is no triangle in this one. So the question is that how many such colorings are there? So I need to find how many such colorings are there. So if you are seeing this problem, what will be your approach? What do you think? Yes, Saranya? Saranya, you raised your hand, is it?
Sir, I've unmute her.
Yeah. Oh, Saranya is not there. Okay, let us check somebody else. And what about let us Sriram or okay? What about unmute?
Sir, my approach would be I think it's only 2.
Only 2.
Yes.
Okay. Only 2. Why 2?
Sir, so first you already showed the outermost and there's a star inside. So if we inverse the color also, it's going to be the same. So
Okay, so there is one more. Yeah, you are right. So there is one more like that one. Yeah, that is correct.
I can build on. I don't know how to build from, but I know that it's going to be more than 2 or 2.
More than 2. This is another color, which is
More than
I do this one and I do this one and this another color. Yes. Okay, then. Anything else? Any other approaches? Let me check whether I can do this 1 minute.
So whom do we unmute?
No.
Sir,
1 second.
I have one more solution.
What is one more? How many are there first? How many are there? That we have to answer, isn't it? How many are there? Let me check whether this is a bit. Okay. How many are there? I have to find how many colorings are there, meaning how many ways I can color this. That's what I want. How do we count? Yeah, 720 different types. So, how is it 720?
There are 3 possible types if there's only one. No. There are 3 Let's simplify this problem. Let's say that we have a normal triangle having 3 points. How many different ways can we color each line? So there, if there's only one red, there can be 3 possible ways. Similarly, we can reflect everything for another 3. We will come up to 6. But now we need to find how many possible triangles are there. We'll multiply it by the number of possible triangles and then we'll find the answer.
So you multiply with the number of triangles. Okay, you said for any triangle, one triangle. So I have to color that in such a way that it's not of same color. So these two could be red and this is black and then like that. How many ways you are saying?
6 ways per
6 ways. Okay,
triangle.
then 6 ways. So I have 5 points. And then if I choose any 3 of them, and then any 3 points, I know that they are not on the same line. Therefore, they will form a triangle, right?
Yeah.
So that
Any
means
3
there are,
points can form a triangle.
okay, there are 10 triangles in this one. There are 10 triangles here.
That means the answer is 60.
Okay, 10 into 6, it is 60, correct? Is that the right answer?
I think so.
Does it make sense that why should I multiply by 10? For example, if I have a triangle like this, I have like this one. So I have another triangle here like this one. I have another triangle like this one. So this one is colored like this is red, this is red, this is black. And then here in coloring this triangle, I have already colored this guy. So I have only 2 shades color, right? So if this is 6 ways and this is not another 6 ways at all, because I already have colored one side in this other coloring. So this 10 into 6, it looks a bit off key, isn't it? Okay, let's look at one way of doing this one. Take any one of the points. If we have 3, how many lines emanate from each vertex? Meaning each of these points. So I have to join them to other 4 of them, right? Join them to other 4 of them. So if 3 of them are of the same color, suppose that from a vertex, from any one point, if 3 are of the same color, so what does it mean? I have these 3 are same color. Now look at the other end of this one, this end, and this end. And suppose these 3 are all red, let us say. If any one of them is red, what will happen? If any one of them is red, suppose this is red, then these two are already red, so they have a red triangle. So this cannot be red. And if this is red, again I have one more triangle like this red. So this cannot be red and this cannot be red. So this is not red, this is not red, this is not red. Therefore, all of them should be blue. That means I have a blue triangle here. I have a blue triangle here. So if I have three lines starting from a vertex, if they are of the same color, that coloring will always have one triangle whose sides have same color. Is it right? Is it understandable? Hmm? So if I have that color, if I have any one line, any one point, any one of the points, so three of them are the same color, then I will definitely have a triangle. So what I have to count is that. So what does it mean? That means in each point there can be exactly two red and two blue. It can't be three means what? Suppose if red is one means the blue will be three. Therefore, suppose if I want a coloring in which none of the triangles appear with the same side colors, then that means every vertex must have exactly two red and then two blue. Up to this is fine. Is there any doubts about this? How many of you are not following that one? Raise your hands. Up to this. I have not just made one small observation, that's all. If I have three of the same color, then definitely they will have a triangle. Therefore, I can't have three, therefore only two and two. Yes, Sriram.
Sir, I did not understand like what was the observation. I did not
Now the observation is that if I have three of the same color, suppose I have one point. If I have four lines emanating from that one. If I have three of them are the same color, let us say red. Then I looked at the other end points of those three colors. Then if I join them, if any one of them is red, I have a red triangle. So this cannot be red, this cannot be red, this cannot be red. That means this will be blue, this will be blue, this will be blue. So I will have then a blue triangle. So the conclusion was that if I have three lines joining from any one point, if they are of the same color, then I will definitely have one triangle with same colors. That was the observation. Correct? But what I want the number of colorings in which there are no such triangles. So what I should do? I should have only two of the same color. So I should have two red and then two blue. Is it okay now? Sriram? Yes, no. Hello.
Yes, sir.
Yes. Okay. Now how do we count? So what I have to count now? I have to count that every vertex there are only two colors. So I'm going to try to color them. Okay. Let me see how to color them. So I know that at each vertex there are only two colors. Suppose take this vertex. I have this is red and this is red and this is blue and this is blue. Now note that this side, it can't be red because what I am trying to do, I am trying to find the colorings in which there are no triangles with same color sides. With same color sides. So instead of saying every time no triangle with same color sides, let us say such a triangle is called a monochromatic. That is same color. So that means what I'm trying to find I'm trying to find number of colorings such that it has no monochromatic triangles. That's what I'm trying to find. Okay, now I know that one condition was that at every point there must be exactly two sides of one color and two sides of the other color. Now let us check this one. So I have this is red and this is red, and this must be blue, and these two are blue, therefore this must be red. Now let us look at what happens if this guy, that is I have already said, I have already colored 4 of the sides like this, and then these two are like this, and then already know that this one has to be red and this one has to be blue. I already did that. Now what about the color of this thing? This could be either red or blue. So if it is red, if this is red, look at this vertex. Look at this vertex. This vertex, there is already one red color and another red color. Therefore, these other two things must be blue. So this must be blue and this must be blue. So I have already found out that this is blue. And so once this is blue, let us look at this vertex now. The other vertex. This vertex I have already one red and then two blues. Therefore, this must be red. So this must be red. Correct. So I have already fixed out this is red, this is red. Now I have already said that this is red, this is red. All the things have been colored. So note that this coloring, so this coloring has no chromatic triangles, monochromatic triangles. So this is one way of doing this. Now we looked at the case when this thing is red. Suppose if this is blue, let us say. So this side could be red or blue. This is blue, let us say. If this is blue, let us see what will happen to this side. What will happen to this side? So already I have two blue things. I already two blue things. So there must be, this must be red. This must be red. So this must be red. So this has to be red. This has to be red. I already have two red things. So note that if this is red, what will happen? This is red, and this is also red. Therefore, this vertex has three red things. Three red things. So this is not possible. I already know that if there are three red lines emanating from vertex, therefore it can't be. So therefore this cannot be blue. This cannot be blue. Correct? This cannot be blue. So I have this is red, and one thing I heard what was that this is red, and then I already saw that this is blue. Now if this is red, then I can do one more thing. So this can be red and this can be red. So this is another coloring. For the same thing, I have two coloring. So this is one coloring. This is one coloring. This is second coloring. So if I take these two are red and these two are blue, I get two colorings. Okay. Now, what are the possibilities for this one, for this top vertex? So these two could be red, and then these two could be blue. Sorry, these two could be blue, or this could be red, and then this could be blue, this could be blue, or this could be red, sorry, this could be red, and that could be red, the other two could be blue, or this could be blue, sorry, this could be blue, this could be blue, the other two could be red, or this could be blue, this could be blue, so these two could be red, or this could be, sorry, or this could be blue, this could be blue, the remaining two is red. So these are the only 6 things. So I have 4 lines. I have to choose 2 of them to be red and then 2 of them to be blue. So these are the 6 ways of coloring the first vertex. For this one, I have 2 colorings. For this one, I have 2 colorings. This 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 I have 2 colors. Totally, how many will be there now? There will be 12 colorings. There will be 12 colorings. So now, if I have like this, I have all these 12 colorings here. That's what I have done. So what did we use here? We just used simple counting argument. Did I use any fancy theorems? Did I use anything which you didn't know just before this one? Did anyone? Okay, is there any doubts in this proof? Any doubts? Did you understand correctly all of this, what I did? See the whole, yes, Tasha.
I
Yeah.
couldn't understand how can you get it like if you put an outside border of a different color like red and
Mm-hmm.
put an inside color of blue,
Mm-hmm.
not a triangle cannot be made, right? Or
No. See, I have to color all. See, I have these two are the same color, and then this is the same color, right?
no, I couldn't understand how could we put like we can keep in that way also, right?
Why? I can keep it in this way. Means, see, for I have 4 of them, 2 must be chosen to be red and 2 must be chosen to be blue, right? This is another choice, isn't it?
But
Hmm.
I still couldn't get it like
Get it what?
it'll be like
So
that.
in this case, for instance, this has to be red, right? This has to be red.
Yeah.
Then this could be either blue or red. If I say this is blue, so this is red, the same argument will work. Meaning the whatever I did for these two, whatever I did for this one, the same argument works. Only thing is slightly different triangles I have to check. If this is red, then what I already have a 2 red here. Therefore, I have to have 2 of them blue. So that means this must be blue and then this must be blue. Correct? And I already have this is red and then two blue already there. So this has to be automatically red. Done. And what about this one? This can't be red, therefore this has to be blue. Done.
Every line inside can be blue,
Yes, every line inside will be blue, all the outside will be red.
but we cannot rotate it.
Why should I rotate?
Like we can tell the different sides.
No, that's what I said. So all for every time I choose 2 of them to be red and 2 of them to be blue, I get 2 colorings in which there are no monochromatic triangles. So I have chosen all the 6 ways of doing this. 6 ways of coloring, 2 from here. And for all the 6, I have got these colorings. So therefore, I have 12 of them totally, right?
Okay, thank you.
Yeah, so that's what. So this is a simple problem. And then if you see that, what did we use? We just use only one observation. That is, if there are three lines of the same color from one point, then such a coloring is not good. Such a coloring is not good. So is not good. So what I should do, I should just look at only the colorings in which there are only 2 lines of the same color. And of course, since I have 2 colors, there should be 2 of red and 2 of blue. That's it. So that's the only observation which I have to make. After it is a very simple counting. That's all. Correct? It's a simple counting principle. Right. So the kind of arguments which we use here will definitely you will learn more about this kind of stuff as we go along. Now let's look at that was an IOQM problem. Let's look at an RMO problem, 2015, which is about 10 years back. So these days, this will not be a RMO level problem. This will be more of an IOQM level problem. So here we have 28 objects placed along a circle at equal distances. And how many ways I can choose 3 objects to be chosen from them so that no 2 of them are adjacent or diametrically opposite. No 2 of them are adjacent or diametrically opposite. This 28 is a large number. So let's look at what will happen if I have only 10. Suppose I have only 10 points, let us say. I have a regular polygon of 10 points, 10 vertices. I want to choose 3 vertices. No 2 are adjacent or diametrically opposite. Suppose if I choose, let us say, 1, 4, and 8. Is that okay? No 2 are adjacent? and no to a diametrical opposite, because the diametrical opposite to this one is this point. Diametrical opposite this one is this point, and this one this one. So no, none of them was chosen. So this is one choice. So it is 1, 4, and 8 is one choice. Similarly, I can choose 2, say 6, 5, and 2, 5, and say 9. So 2, 5, and 9 is another choice. Like this. So how many such choices will be there? How many such choices are there? Yes, let's look at any, yeah. So any, yes, Ranya.
Sir, actually, when you choose 148 and 259, I got a pattern that if you join those 3 points, it makes a triangle.
Okay, that triangle, that's correct. Then, so what's the observation? 1, 4, 8, isn't it? This is what I suppose. Yeah. So this is a triangle, yes. So even if I choose 2, this one, and then this also is a triangle, right? This also is a triangle. That is my 2, 7, and 4. But 2 and 7 are diametrically opposite, isn't it? 2 and 7 are diametrically opposite. So we cannot do that. So any other observation? So how do we count? Yes, Hemdev, yeah.
I think they found a solution.
Mm-hmm.
We'll find a number of combinations where the number of triangles which have one wait, let me, yeah, which the number of triangles with these 10 points. Then we'll count the number of triangles which have the diagonals, and then we'll subtract.
Okay.
I will say the entire solution throughout.
So
Okay.
number of triangles. First of all, I have to count the number of triangles. So the triangles, will you include the triangle like this one? For instance, like this triangle?
I will include it at the first, but
No, you cannot,
I'll
no, you
subtract
cannot
that
use,
triangle
no, you
from
cannot
that.
use this triangle because these were adjacent, right?
Sir, I know, so I'll subtract.
Huh?
I know, so I'll subtract that triangle from
That triangle also.
adjacent.
So first, what will you count? You said that you're going to subtract something, but what, from which one you were going to subtract?
From the number of triangles which
Number of triangles.
which the entire thing has.
That, no, number of triangles in which no side must be a side, right?
Yeah.
I can't use this kind of, how will I count that first?
We'll count all triangles and we'll subtract the ones with opposite sides.
Okay.
Opposite points.
That's a good idea. So we'll find all the triangles and that's fine. Okay. Mm-hmm.
But then
Yeah.
the answer will turn very big.
Oh. So that's going to be a bit of a problem, isn't it?
Yeah.
Okay. So any other idea? Yes, Yogi.
So I'll solve in the way.
Huh?
And then I'll give the answer. I'll
Give
just solve
the,
it for now.
which one? How? You tell me the method. I don't want this answer anyway. What's the method you used? Hmm? What's the
Sir,
method?
we can take 10, 7 and 3 no.
Huh?
We can take a triangle 10, 7 and 3.
That is one of them. But I want to find how many are there.
Okay, sir.
Yes, Bharat?
Sir, can I show the images? Image what I made. Can I show
You
the
have
image
what?
what I made?
You have what?
I have made a drawing of that. So can I show it?
Okay. I don't know whether you will be able to show that, but okay, you can let me try. Okay, you can show the camera.
Is it visible? Oh, yeah. Sir, is it visible?
Not necessarily. Okay, go ahead.
So, sir, we can take the alternate points means from 1
Mm-hmm.
to 2
Mm-hmm.
or 10.
Mm-hmm.
So like this we can make 1 9 and 3, 1
Mm-hmm.
8 and 4, 1 7 and 5, and 1 C. Sir, here one point is remaining. So 1 6 and 3, or 1 6 or
Mm-hmm.
10.
Mm-hmm.
So like this we are making nine images.
Mm-hmm.
So from as we are making 9 images from each point, so but 10 points we can make 90 images.
Mm. So looks promising, but it's a lot of counting, isn't it?
Yes, sir.
What about Siddharth?
So, sir,
Mm.
actually, this is not really like a method, but then I found an observation
Mm-hmm.
that if a triangle like that is true, then it
Mm-hmm.
must be isosceles.
Not necessarily. For example, let me show you. It's not necessarily isosceles. For instance, I have, let us say, this one and this one. Oops, it becomes isosceles, isn't it? Here it's a bit of a problem, but let me check. Yeah, this one is isosceles. No, no, it's isosceles. Yeah, okay, even granting that then. So you're going to find all the isosceles triangles, right? But does it work for 28 also? Will it work for 28? I don't know. Okay, let's look at Saks Chopra.
So for the 10 dots, can't we
Hmm.
just, so there are 8 possible points that we can connect to from 1 if we're choosing one other point. So can you show the image for
Mm-hmm.
10?
Hmm.
So from, let's say from 1, if we
Hmm.
take one more point, we can do 8 different points. We can like
8
make,
different,
no,
okay.
sorry. So we can connect it to 6 more as the point, right? No, wait. So one sec. So let's take 1
Hmm.
and 4. So we can connect this to,
Mm-hmm.
so we can make 4 triangles with a pair of 1 and 4.
Hmm.
So just like that, if we take all the pairs and
Hmm.
multiply it by 4, we can find the number of triangles.
Yeah, but will it work for 28 also?
So I'm not sure if it'll work for 28.
Hmm. So here the idea is, so let me just show you. So most of the time, just as in the previous problem, the main thing is that you have to observe something very critical. You have to observe something very critical. So since I cannot count this directly, I'm going to count the complement. What is the complement? The complement is I'm going to find out meaning all triples of points such that they are either what? They are either contains three consecutive points, or a pair of diametrically opposite points, or pair of diametrically opposite. Now I have 10 points, let us say. I have 10 points. So the first point can be chosen in any of the 10 ways, right? Any of the 10 ways. The second point can be chosen in any of the 9 ways. The third point can be chosen in 8 ways. But if I just choose, let us say, 1, say 4, and then 8, this choice will come in several ways. It could be coming in 1, 8, and 4, or 4, 1, and 8, or 4, 8, and 1, or 8, 1, and 4, or 8, 4, and 1. So if I just multiply like this, so each choice will be counted 6 times here. So if I just divide by 6, this will be the number. So this is 10 into 9 into 8 by 1 into 2 into 3 ways of choosing 3 points. Choosing 3 points, correct? Of this, how many will have 3 consecutive things? Let us check. It will be 1, 2 and 3, or 2, 3 and 4, or 3, 4 and 5, or 4, 5 and 6, and so on up to 10, 1 and 2. So there are 10 of them which are consecutive. So out of this 10 into 9 into 8 by 1 into 2 into 3, which is equal to, let me check this one, this is 120. And if I just subtract this 10 of them, this is 110. What is this 110? 110 gives me the number of triples of points such that no two are consecutive. Correct? No three are consecutive. Correct? No three are consecutive. Isn't it? Okay, so what more I have to do? What more I have to do here? So I have 3 of them consecutive. Now I have to also eliminate 2 of them consecutive. That means I have these 10 of them. I have this 10 of them. So 2 of them consecutive means I can choose 1 and 2. If I choose 3, I would have already counted in the other one. I already chosen that one. I can't count, I can't do 4. So if I choose 1 and 2, I can choose any one of the 6 points. So for this pair, I have 6 of them. And for this pair, I have 6 of them. So similarly for I have this one, I have 6 of them. So I have 10 into 6, 60 of them in which 2 are consecutive. So I will subtract that also. So I have, so 110 minus already, sorry, 120 minus 10, 120 minus 10 in which 3 are consecutive, minus 60 which are 2 are consecutive. So 120 minus 60, this is 50. This 50 will still contain something. What does it contain? It will contain a pair of diametrically opposite also. That also I have to subtract. So let us see how many diagonals are there here. There are 5 diagonals. 1, 2, 3, 4, and 5 diagonals. So if I choose any one of those diagonals, suppose let us choose this diagonal. And that means I choose this one and I choose this one. Then I have to find out all the things which are not excluded. So 2 is not chosen, 10 is not chosen, this is not chosen, this is not chosen. For this diameter, so I have 2 plus 2, 4 choices. So for every diameter, I have 4 of them choices. So I have 5 diameters. So I still have to subtract from this 50. I have to subtract 20. That will be 30. So for the 10 case, I have 30. Let me repeat. So what I did was, first I found out how many ways I can choose 3 out of 10 points. 3 out of 10 points. That's the first step. So I said there are 3 steps in this one. First step is that I chose, first one is that how many ways I can choose 3 out of 10. This was 10 into 9 into 8 by 1 into 2 into 3. Second one, I chose how many are all the 3 consecutive, all the 3 adjacent. This is basically 10 of them. Then 3, 2 are adjacent. 2 are adjacent. So this we saw that one. Okay. And then we have to just, how many are? 2 are diametrically opposite. 2 are diametrically opposite. So we subtracted from this one, and this one. Then we got the count. And the same thing could be done for 28 also. So it will be 28 into 27 into 26 by 1 into 2 into 3 minus etc. etc. So this is the basic idea. The computation is not very important. So the idea is that we just looked at the counting the complement. This is a very useful technique in counting, which comes pretty often. And then that technique we will, of course, you have to master that one, and then we will see a lot of examples of that step as well. Now let's look at this problem from INMO. We have 2016 points on the circumference of a circle are colored red. The remaining points are colored blue. Show that for any natural number 3, the n greater than or equal to 3, there's a regular n-sided polygon, all of whose vertices are blue. All of whose vertices are blue. So let me show an example here. And where is that one? Yeah. So here I have, instead of 2016 points, what I have done is I have just marked some 10 points or 10 points on that one. Now, these 10 points, what I have to show is that I have to show that there is a regular triangle, equal triangle, all of whose vertices are blue. For instance, in this case, it's very easy. So here I have, this is, sorry. So I have, sorry. Undo. Yeah, undo. Yes. So I have this one line segment. So here at least I can, but so I can just use this line. Oops. 1 minute. This is behaving a bit badly. 1 second. Sorry. Okay. Now I have to delete all these guys. Just met. So now if I have a triangle here, if I rotate that, what happens? How many triangles I will get? If I rotate this triangle inside that circle, how many triangles I will get? If I rotate the triangle? Yes, Kamina. Kamina?
Sir, I had raised hand for the previous question.
We have? You have what? No, you have a question of the previous question. What's the question? I couldn't hear you. Where is Kamina? Okay, yes, Hemdev.
Sir, I understood that previous question.
Okay, yeah. Okay, right. Now this one, in this question, so if I have this circle and then I have only 2016 of the points are colored red, and if I just look at any regular polygon of side, let us,
Sir, is the answer for the second question 2266?
266,
226.
2266.
Yeah.
Yeah, that's correct. Yeah, actually see what see,
And
what
what
I'm
does the
what
third
I'm
question mean?
huh?
And what does the third question mean?
Third question is that I have 2016 points on the circle are colored red and the remaining are colored blue. Okay. And take any n, for instance, suppose n is 10. Show that there is a regular polygon of 10 sides such that all the vertices are blue. It will be for even if it is 10,000 sides. All the vertices are blue. So how many points are there on the circle? How many points are there in the circle? How many are there in the circle? Yes, I am there. How many are there on the circle?
7.
No. How many points are there on the circle? Suppose
2,
we give 2016 points are colored red.
Yeah.
But how many points are there in the circle?
2016 plus n.
plus n.
Yeah.
Why n? Why n?
Because they are n at
No. Let me ask a different question.
least
Suppose I have a line. Suppose I have a line like
9.
this. How many points are there in this?
What, sir?
Suppose I have a line like this. How many points are there in this?
Infinity.
Infinity. Right? Similar to circle also, right?
Yeah.
Circle also there are infinitely many points. So circle also there are infinitely many points. What about Kavinan? Yes, Kavinan. Kavinan? I asked you to unmute. Yeah.
So,
Hmm?
I was also about to tell that there were infinitely many.
Infinitely many points. Yes. Okay, there are infinitely many points, of which I have only 2016 of them are colored red. So if I just draw a square like this and then start rotating that one, how many squares I can get?
Infinite.
Infinite. But these are all these squares. If at all there is a vertex which is red, then how many such vertices will be red? Only 2016 of those squares
You'll
of the
have one vertex
squares
is red.
will have one vertex red, one or more vertex red, but I have infinitely many of them, out of which only 2016 are bad. So there are infinitely many which are real good. So the same thing, what happens for square happens for any regular polygon as well. So it's a very simple problem, in fact, even though it is 2016, but the crux is that it is difficult to write down. The proof is difficult to write down. But anyway, so we got the central idea. So this is about infinite versus finite. Instead of 2016, if I say 10 power 10 power 10 power 10 points are red, still the same conclusion holds? Will it have the same conclusion? Will it be the same way that there will be, for any n, there will be a polygon which is like that? It will be same, right? Because there are only finite ones. Any finite number, it could be, let us say 2016 power 2016 power 2016, all that thing, 2016 power 2016 power 2016, etc. So this one up to, let us say, 2016 of them. Even then it is finite. And there are infinitely many points which are blue and so on. So that's what this problem is about. And one, since I have only very less time, let me do one last problem in IMO 1993. Here we have an infinite chessboard. Okay, infinite chessboard, and then in this infinite chessboard, like this. So I have a n square pieces occupying a side. So I have a square of side n. Let us say a square of side n here. So taken 4. And each of those cells, I have one piece. I have one coin, let us say. And all the other cells are empty. All the other cells are empty. Now I'm going to play a game. You know that solitaire game is played similar to this one. So what I will do is that I will, suppose I have two things like this and this is empty. So I jump this coin to this one and put the coin here and erase this and this one. Similarly, I can do, so this one is jumped here and then I can erase this and this. So this will be the coin here. So I can keep on doing this one. If I keep on doing this, so I can do this also from here to here. So this will be there and then these two can be erased. And again, I can jump like this and then these two can be erased and I'll put like this. So if I just do that, the one, of course, we already know that. So it is moved to jump unoccupied square and then has been over is removed. For which values of n, can the game end with only one piece remaining on the board? One piece remaining on the board. So for instance, suppose I have 2 by 2. So I have like this. Now what I can do, I can just jump like this and put it here and then remove these two. Then I can jump like this and put it here and remove these two. And now I can jump like this and then put it here and remove these two. Remove these two. So for n is equal to 2, the game does end with one piece. Correct? Game does end with one piece. Similarly, for n is equal to 4, then also I can do that. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So I can jump like this and then do this and so on. So you can just check that for 4 by 4 also this works. Let's check for 3 by 3. You have like this. Now I can jump like this one. So put a coin here and then erase this one and this one. And similarly, I can jump here and then erase these two and put a coin here. Now I can again jump here and then put a coin here and then erase these two. Oops, sorry. Like this. Again, I can just jump like this one. So I can here, then I can erase these two. And I can jump here and then erase these two. Erase these two. Here. Now I am ending with 4 and no more move is possible. Correct? Because all of them are disjoint. So no more move. So I'm ending with 4 here. I'm ending with 4 here. Okay. So the question is that for which values of n we'll be able to end with only one piece. No, let us try this one. So suppose I have an empty square here and a 3 here and this here. Then what I will do is that, so from here, I will jump here and remove this. And again, I will jump here. Sorry, I'll jump here and remove these two. And then again, I can jump here and then remove this. That means if I have an L type of coins, I can delete these 3 and then end up again with just one piece. Suppose I have any L like this and this is to be empty. If this is empty, I can remove this one. So suppose I have a 4 by 4 here. So I have a L here and this one is empty. So I can remove this. And again I have a L here. This one is empty. I can remove this. And now I have a L here and then this one is empty. So I can remove this. I have a L here. So this one is empty. So I can remove this. And again I have L here. So I remove this. So for 4 by 4 also works. For 4 by 4 also works. Correct? Right. So any questions up to this? Yes, Hemdev. Hemdev?
Sir, I found out that there can be n minus. For it to work, we need, if it is possible, we need n square minus 1 possible moves to make it to from n
Yeah,
square to 1.
that may be okay. But what I want is our question is to find which values of n I can end up with one piece.
I thought that was in the way.
Okay, let's say Tarshan Sagar. Yeah.
Can this be something like Chinese checkers in a
This
L
is
formation?
like Chinese checkers, but the thing is that our question is to find the value of n. This is like Chinese checkers, yes.
But is there any other pattern other than L we can use?
Maybe.
Yes.
Yes, Kavindra.
Sir, is it
So
like all when n is like any even number it works?
N is any even number, it works. You can try for n is equal to 6.
we can also use previous ways like the 2 version or the 4 version. We can use those.
2 version, 4 version I have checked. Okay.
We can use
So,
those also.
huh?
We can use those also.
Yeah, we can. No, we know that 4 by 4 works, 2 by 2 works. I don't know whether 3 by 3 by 3. I probably would have made a mistake and ended up with 4 of
3
them
by
instead of
3 might not working
3 by
because
3 is
with
not
the
working.
else
Huh.
because with the else we will always get one remain. We'll always get if we like do an L. We'll try. Let's see how many L's are
No, if I
possible.
have 3 by 3, so I have an L like this. So I can remove this guy. And I have like this one. And I have an L like this. I can remove this one. Then I have only 3 left. Now if I just remove like this, so this will go away. But I am left with 2 things, not 1. There's no, at some point in time, I am left with only just 3 consecutive things in one line. Right?
Yes, sir.
Yeah. So probably I think yeah. Anyway, so let's come back to it. So 4 by 4, I know that it is works. What other things it will work?
So we can first do the 2 by 2 and then do another 2 by 2. So any
Another 2
even
by
number
2.
2 by 2 and then duplicate it throughout the even
2
and
by
then
2,
we can
another.
do.
No. I have 2 by 2. So I have this 2 by 2. Which 2 by 2 you want? If I take this 2 by 2.
Yeah. The
Ah.
once starting from the corner we'll go.
What will happen is that this, if I just remove like this one, I will have one thing left like this. One thing left like this one. So that will be a problem then. But anyway, we'll come back to that. So let's since I
Now
have
we
very
can
less.
do something. Oh, I understand.
Okay. Right. Any other? Yes, Bharat.
Sir, to the power of 2 means 2 to the power of 4 or 2 to the power of 3.
You mean to say that all the powers of 2 will work?
Yes.
Okay. Let us check what are the things which are working and which are not working. Now let us look at this closely. What we did for 4 by 4. So when I started with 4 by 4 like this, where did I end up with? I ended up with bottom thing like this. This is the one, right? I ended up with bottom thing like this one. So that means if I just do this L business in 4 by 4, I can remove all of this. I can remove all of this and leave with one in this one. Now let's look at, that means what I have 4 by 4 like this one. So I can remove all of them with, sorry, what I'm saying, and leave with only this.